Alright, I guess we're up and running. So linear regression. We've talked about correlation. Correlation is a way to talk about the relationship between two things, but a more complete model is that line. Linear regression is the line. It's the line and talking about how far are the dots from the line and how good is the line and what color is the line and does the line really like me. I mean, I talked to the line and the line texted me once or twice, but I'm not sure if she really... Okay. Here's a joke about regression. We'll run into this later. It's about extrapolating beyond your data and coming up with ridiculous conclusions. So what's regression analysis? It's building models of relationships between variables. Now, partly you just have to get used to mathematical models. You just have to get used to this concept. A model is an abstract thing that doesn't exist in the real world. It's purely theoretical. It's too perfect and wonderful to exist. It's like the perfect prototype of the perfect boyfriend or girlfriend. It exists and it's perfect, but only in your mind. Real boyfriends and girlfriends will always be different to some extent. And different means worse because the perfect boyfriend or girlfriend is perfect, right? So you have the model of the boyfriend and girlfriend. Anyway, we make models of relationships. And linear regression is about very simple models, which you might say, how silly, we should have complicated models. Well, sometimes you do need complicated models, like when you're trying to model a weather pattern. But sometimes a very simple model can be extremely useful for helping us understand something. Admittedly, sometimes a straight line relationship doesn't work. But linear regression, simple linear regression, two variables, straight line. There's a whole world of regression, and a lot of it's called linear, but we're talking about simple linear regression here, a straight line relationship. It's just representing the relationship between two variables with a straight line on a scatter plot, or an equation that describes a straight line. They're both just different ways of doing it. So what do we do with it? Well, we find the best straight line that represents our relationship, and we say that's our model of the relationship. Then we use that model sometimes to describe the relationship. We usually do something like we judge how good a fit that model is to the actual data. So it's like saying, I have this prototype of the perfect boyfriend or the perfect girlfriend. Well, here's a real person. Okay, so how good is this prototype, this mental image of the perfect person? How well does that fit this real person in front of me? What are the differences? That's the same thing. We have this model that describes in a very hypothetical and abstract and perfect way a perfect straight line, some relationship, and then we look at our actual data and we say, how well did that model really describe our data? And then we often take this final step of testing the statistical significance of this model, which means we look at the model and we say, how likely is it not only that the model fits our data, but that the model fits the data in the population, that this model describes the relationship that's in the population between all the observations, not just our little sample. So is our model describing just a fluke relationship, or is our model describing something real from the population? So I don't know if these are really steps. Regression is different from other analyses, and it becomes a different thing where it's like a toolbox full of some tools. Sometimes you pull out one tool, sometimes you pull out another one. It always involves creating a model to describe the sample. Regression is always has the model. And since it's a straight line, mathematically, you only need two things to describe a straight line. Therefore, you only need two things to describe a straight line model. You need a y-intercept, and you need a slope. We call those A and B. Now, I'll have some comments on terminology later on. So sometimes we inspect and use the model to do things. We usually consider whether we violated conditions. Just like ANOVA, just like t-test, etc. Sometimes there are conditions that need to be considered, or almost always. There are conditions that need to be considered, and we need to look and see if we're violating those conditions to see whether we can use this at all. We are interested in the concept of outliers, which are individual observations in our data set that are very, very different from the average observation. And because they're so very different, because of the nature of the way the math works, they can have a disproportionate influence. Kind of like an extremely rich person who lives in your little town. When you're voting, the really rich person might get a lot more attention from everybody because they're super, super rich. Well, that person is kind of like an outlier. An outlier is like a heavyweight, a fat cat that's, since it's so far away from everything else, so different from everything else, it exerts too much influence. Sometimes we use the model to predict values that don't actually exist in our data. So we can say, well, our model says that, for every 1 unit, for 1 liter of milk a person drinks, per day, then they'll grow an extra, 2 centimeters by the time they're 12. So what would we predict would happen if a person were to drink 1.5 liters of milk a day? How many centimeters would they grow? We do that kind of thing. And then we often evaluate the fit of the model. We see whether it is a good fit with our data, if it describes our data well. We have these concepts called residuals, which describe the badness of fit. We saw those. They were the red dashed lines in a previous slide. We use R and R squared. Those tell us how good our fit is. And then we often test whether our model is likely to have occurred under the null hypothesis where there's no relationship. I mean, how well does this describe population data? How likely is it that this came from a population of a certain characteristic? So we statistically test the significance of B and A. Testing B is the same as testing R or R squared. So the equation for a model is really simple. You just say the y value on this graph, whatever the y value is the y-intercept plus the slope times the x value. You're familiar with this. Y equals mx plus b, it's sometimes put. We say y equals ax plus b. So we use different symbols here. There's a true relationship, a relationship between the population variables, all the variables, or sorry, not all the variables, all the observations in the variable. So if you say, we're talking about the relationship between number of policemen per capita and crime per capita, well then you're thinking, this describes that relationship in all cities in the whole world, well, however we define our population, maybe all cities in North America, which is thousands of cities. And so y has a hat, which means predicted y, because the line isn't going to be on the dots. It's going to be near the dots, but it's probably not going to be on the dots. So all these values are predicted y values. This describes a line. All the dots on it are on a straight line. So the y values aren't real y values, they're predicted y values. We use real x values, but then we multiply them by some b, by some slope, and then we add some intercept, a, and we get a predicted y value, not a real y value. And we use different symbols when we're talking about actual data, and this is much more common. We say ax plus, or a plus bx, the intercept and the slope. So let's remember lines. Lines are pretty important. Here's a line. What's the equation that describes this line? Totally abstract. This is going back to high school algebra. Well, the intercept is 3 because that's where the line crosses the y-axis. It's a positive 3. And to figure out the slope, we can take any chunk of the line and figure out how far it went left to right and how far it went up to down and up and down and divide those things. So the change in y, delta y, is, sorry, not 0.3, it's positive 3. So y went up 3 in this one section that we're looking at, and it went over 3. So rise over run, we sometimes say, to calculate a slope of a line. In the change in y over the change in x, so 3 divided by 3, that's 1. So the slope is 1. So we have an intercept and a slope, and so then we would, in regression terms, we would say y hat equals 3 plus 1x. 1 is the slope, 3 is the y-intercept. So here's another example. See if you can work it out for yourself. The intercept is 3 again, but now we have to pick some kind of a space to calculate how far it goes right for every time it goes up or whatever. In this space, doesn't matter which space, we took a space of a change in, oh, I'm sorry, this is, hang on. I think I made a little bit of a Mr. Error there. So we're continuing here. I pushed the, all right, let's rectify one of my many mistakes. The change in y is 2. Along the course of the line from here to here, y went up by 2. It went from 3, and here it's at 5, so it went up 2. The intercept is 3. And change in y is positive 2 over that span, and in the span where it went 2 up, it also went 10 to the right. So 2 up for every 10 to the right is 0.2 up for every 1 to the right. So the slope is how many up for every 1 to the right. Rise over run. So we divide that out, and we get y hat equals 3, the intercept, plus 0.2x. Here's another example. And I'll talk about the solution now. The intercept is 6. And you can look at where it crossed the two axes is a nice convenient chunk of the line. It went down by 6. So going from left to right, the line went down by 6, negative 6, change in y, over the space where it went up by 3 in x. So negative 6 divided by positive 3 is negative 2. So y hat equals 6 minus 2x. Here's another one, intercept of 3. change in y of negative 6 again, but for the change in negative 6, it actually had to go 12 to the right to get the same change in negative 6 here. So 6 divided by 12, negative 6 divided by 12, negative 1/2. So predicted y is 6 minus 0.5x. This is a puzzler, unless you remember your college algebra. So the intercept is 5. Change in y is 0. It changes nothing. And the change in x is infinite. It just keeps going and going and going, forever and ever. So the slope is undefined. It's 0 divided by infinity. It's undefined. So the equation isn't an equation. It's just, well, y equals 5. And this is similar. There's no intercept. There's infinite y. But there's a change in x of 10, so the slope is totally undefined, but we could just say x equals 10. Now that doesn't happen in real regression. That's just kind of mathematically remembering the way lines work. So when we apply the formula to real data, and we get that model, we use this formula to find the best line. So let's look at exam scores and class grades. So we've got on the x-axis here the letter grade so far in the course. This was a couple of years ago in this stats class. And here's the percent they received on the midterm exam. So that green line is the best fitting regression line. That green line describes the relationship between their letter grade and their exam percent. But we're missing a lot of data there. So let's put the rest of that data in there. First of all, this graph pulls a dirty trick that a lot of graphs do because people think it's aesthetically pleasing. They put 0 a little over to the right from the left axis. So that isn't actually 0. That's 0. So if you carried this line down here, you'd say, oh, the intercept is that. But no, the intercept is here. So we have to remember that. So the intercept is about 58, the y-intercept. And we can look at this little chunk. My lines don't line up perfectly, but the change in y over that period was maybe positive 10. It went from about 58 to 68. The change in x is a much bigger chunk of numbers. It's a different scale, but that's okay. You go with whatever scale you have. The change in x is plus 1, so 10 over 1. So the slope is 10. So the equation would be the predicted exam grade is 58 plus 10 times the letter grade. So that's y hat equals 58 plus 10x. But in real data, we put the names of the variables instead of y and x. And it's exam grade, but it's always predicted exam grade. So instead of putting exam grade hat, which I don't know how to do in PowerPoint, I put predicted exam grade. So this is what the data actually look like, where I got that line from. And then you fit the little best fitting line on there. Not so pretty anymore. It's messy. You can see that some of these people are not described well. This person has a F, a total failing F in the course so far, but they got a 90 or something on the exam. This model does not describe them well. They're so far from that green line. But this person here, they're described pretty well. They're really close to the green line. So we can throw that that equation in there, and we can kind of see that the equation fits, but the line itself, yeah, it's a line, but that model and that equation and that line, they don't fit the data very well in some cases. It's some fit and some not fit. It's always the case. Here's another example. Here's the car data. Here's another example where we can see that a straight line might not fit very well, but it would be a negative situation going down there. Here's its negative association between car price and efficiency, as we've seen before. So here's a least squares regression line between the log transformed abundance of carnivores for every 10,000 kilograms of prey animals like bunnies and the carnivore's mass. In general, the bigger the carnivore is, like you're going up from like, you know, attack shrews or something like that up to tigers, the bigger they are, the fewer of them there are per bunny, which makes sense because otherwise the bunnies would all get eaten up. Here's another one, IQ score, and this is unrealistic. There are not that many people with IQs of like 130. It's really not that common, unless this is just purely the gifted and talented program. And grade point average, I got this out of a book. What kind of grade point average is 0 to 12? Anyway, it's a weird grade point average. Positive association, and you can see some people are not described well. This person, not described well by this model. Let's talk about terminology before we go too much further. The slope in the sample, social scientists almost always call that B, but Open Intro calls it B sub 1. Open Intro follows a mathematical system where there's just coefficients, and they number the coefficients. There's the coefficient 0, coefficient 1, etc. Because you can go further in regression and you can get lots and lots of coefficients, not just a b, but lots and lots of b's. And there are possibilities of, with advanced modeling, of getting multiple a's as well. So they just number them. But social scientists almost always call the slope b. So that's what I'm going to go with. Now, you can standardize that slope. We're not going to talk about this. In social sciences, we do this a lot, but I'm not going to mention it too much in this class because there's only so much time. And when that happens, we call it beta. But I'm going to leave that grade out because we're not going to do that. But in the population, we talk about capital beta, the slope of the regression line describing the pure relationship between two population variables, all the data at once. We call that beta. And then, of course, Open Intro, the mathematical version, they call that beta sub 1. The intercept in the sample, Open Intro calls that beta sub 0. We call it A. So it's A and B, and Open Intro is B0 and B1. In the population, they call it beta 0. We usually call that alpha, okay, capital alpha for the intercept in the population. The correlation, I think it's supposed to be a lowercase beta up here, but every time you turn your back, Microsoft capitalizes everything for you. The correlation coefficient in the sample, Open Intro makes it a big R for some reason. In almost all data analysis, big R is only used when you have multiple predictors. We're not going to do that in this class at all. We use lowercase r to describe just two things together, but Open Intro calls it big R. And then in the population, the correlation coefficient, this is a sample correlation coefficient, that's R. In the population, we use the Greek letter R, which is rho. Looks like a P, it's not a P, it's rho. So these things, anything describing the slope is usually called a regression coefficient in certain circumstances. Beta, just to be confusing because Open Intro calls other things beta. This is also sometimes called lowercase beta, just to screw with your head. This is sometimes lowercase alpha, just to mess with you. And you might recognize capital R as the name of some kind of software we're using in this class or something. But I think that's the software's fault. Big R was around before the software was. This is what we're going to use in this class. We're going to use the social science versions of things. B and A, and R and rho. That's it. That's what we're going to do. And I think we might be finished for this particular lecture, and in future lectures we'll be talking more about regression.